Everyone, good morning. I'm introducing myself. I'm Luigi Palmieri. I'm a PhD student at the third year at the University of Pisa, and I'm currently working with Chiara Boldrini, Lorenzo Valerio, and Andrea Passarella on the topic of fully decentralized federated learning solutions. So as you can see on the background part of my poster, the reason the call for such solutions comes from the exponential growth of data at the edge of the internet that we are nowadays experiencing. In fact, this exponential growth of data is making depending only on centralized solution unsustainable in the medium and long term, meaning that we need some new kind of solutions, and this is where fully decentralized federated learning solution comes in hand, and they take into account peer-to-peer communication network where learners collaborate with their neighbors to achieve a global function. So how does a fully decentralized federated learning algorithm actually works? It works by iterating through three phases. The first phase is the local training part, where the local learners learn about, based on their own local data, and this is usually done by employing a stochastic gradient descent method. Then the local models, after the local training, synchronize and transmit their updates to the network, and then there's an aggregation part where the local learners aggregate the information coming from the neighboring nodes. As you can see, the aggregation strategy is basically a weighted mean of the models coming from the neighboring nodes. So where do we place ourselves in this topic? Our research challenge is about investigating the role of the structural properties of the network on the solutions of fully decentralized federated learning. And so, as you can see in the aggregation strategy, it is heavily relying on the underlying communication network topology. And so we want to explore the impact of the network topology in the decentralized federated learning setting, and how alteration to this initial topology actually affect the learning process. So we here focused on the robustness of decentralized federated learning process. And how did we do that? We achieved that by studying the disruption of the network by removing specific nodes. As you can see, there's a before graph, and then there's an after graph, which is the one after the disruption actually occurs. And we differentiated between two different cases. The case one is the one that we renamed connectivity only, and this is because the nodes that will be removed do not hold any data. So when we remove them, the disrupted network will only lose connectivity. Whereas in case two, the nodes that will be removed also hold some data, and so when we remove them, the disrupted network will experience also a loss of data. And then we studied the behavior of the learning process of the system at different disruption times, coming from the different percentage of accuracy levels of the system. So basically, we achieve a mean accuracy percentage, and then at that point we disrupt the system. And so, and we studied different times at which this happened, or different accuracy percentages, which are basically 0, meaning that the system already starts at disrupted. Then we studied the 70%, 75%, and 80%. And then the baseline, and we confronted them with the baseline, which is the case where no disruption occurs. So as you can see on the right, on the results part, we can see by confronting the mean accuracy of the system, and by the way, we're only showing case 1 results, but these results are true also for case 2. By confronting the mean accuracy of the system at different percentages of accuracy with the baseline, we can see that the difference is really small in the performance, in the overall performance of the system, meaning that we can confidently say that the system is robust to failures. And by looking only at the isolated nodes instead, we can see that by increasing the accuracy percentage at which the disruption occurs, the nodes are able to retain a higher level of accuracy performance, meaning that they are able to to retain some knowledge. So basically we can say that there's knowledge persistence. So the main findings are that the decentralized nature of decentralized federated learning makes it robust to network failures, that there's knowledge persistence, and also that by confronting case 1 and case 2, we can see that the loss of connectivity has a greater impact on the performance degradation of the system than the joint loss of data, meaning that it's more important losing connectivity than losing both connectivity and data.